Hi, my name is Matthew Binder. Welcome to the Australian presentation for the Almond Board of California Irrigation Design Summit. In this presentation, I will go through the following agenda items: irrigation design brief, water source, main filtration, planning almond irrigation, block layouts, submain design, backup filtration, mainline design, valve assembly, energy analysis, system automation, and at the end, I'm happy to take any questions in our Q&A session. Before undertaking any irrigation system plan, I will run through the irrigation design brief form in conjunction with the client. The purpose of this form is to make sure that the client and designer have agreed upon the same things and the desired system outcomes. This form incorporates things such as the job details, the end user details and property details, design details, information submitted either by the client or any third-party companies, automation, soil and water analysis details, and any other additional comments made by either the client or designer in regards to the system specifications. Water source or supplies. In Australia, we have four main types of water supplies: storage dams, channels, rivers, and bores. Each of these supplies or sources have their positives and negatives, but an efficient, healthy irrigation system can be designed with any one of these sources with the right technologies and practices. Main filtration. We use three types of main filtration on our irrigation systems: screen, disc, and media. Each of these filtration types has their benefits, but also has their limitations. When deciding what filtration to use, water quality and water analysis is the first step. Another consideration is the size of the filter station or footprint. In this example, I've shown an equivalent flow rate for each filtration type: screen, disc, and gravel. Things to take note here are the footprint that the filters will take up in the shed, the backflush pressure requirement at the discharge of the filter, and the additional backflush flow required when the filter is backflushing. Planning almond irrigation. When planning our almond irrigation systems, we first need our initial data from surveyors and agronomists. To decide on the property layout, we need to get the ground height contours and any soil surveys. We need the water source type and location, and a water analysis report if possible. We need to make sure and ensure that any soils unsuitable for planting are left vacant in the initial stages. Carrying out soil improvement works, such as ripping, adding in organic matter, or considering bedded mounds on shallow soils. Deciding on how many varieties will be used and whether or not it will be an A, AB, or ABC system. I'll discuss these systems in a further slide. Deciding on the peak water requirement used by the crop and whether or not we are going to plan for a full 24-hour day pumping window or look at a shorter term time during the day to save on power costs and any downtime. In the initial design, we need to make sure to separate any different soil types onto their own individual valves, particularly shallow and deep soils. Discussions with the client on how he or she will use the system, whether it be pulsed over the day or one constant irrigation per day. We want to avoid system layouts that can result in excessive drainage. Minimizing clustering valves or grouping valves that can result in the use of blank submain piping that is likely to drain into low-lying areas. Avoid large submain size pipes that hold a lot of water, particularly 150 ml and above. If flushing submains will lead to additional drainage, use individual drip line taps rather than a collection manifold. For systems being operated more than once per day or pulsing, consider additional system drainage reduction features. Non-leakage drip line, non-return valves in submains, check valves in the drip line, or drainage non-leakage D&L valves, also in the drip line. We have a few advantages of growing almonds here in Australia. Almonds grow quite well on a range of soils, including shallow, limey soils, which we have large quantities of this. We also have moderate salinity, which the crop will cope with. We have large river systems, close to idyllic soil conditions. The irrigation method for almonds, being drip or sprinkler. Drip is most preferred as it allows for early tree establishment, higher irrigation efficiency, reduced irrigation labour, and greater irrigation flexibility. Automated fertigation systems are also maximised, and a crop can typically be gained earlier over sprinkler. Sprinklers, though, do have soil management advantages. With either irrigation system type, we aim to budget for a yearly water requirement of at least 14 megalitres per hectare per annum for maximum production. One aspect of irrigation management in the design phase is valve. With this irrigation management, we would also like to have a water use guide based on evaporation and crop coefficients, and ideally soil moisture monitoring systems to help with irrigation. Block layouts. When looking at block layouts, we typically design to a maximum of 100 ml backup or check filter size flow rate. This is per one irrigation valve. This ensures us a maximum submain size of no greater than 150 millimeters, which is only necessary if the valve is end-fed of the submain. We also look at a maximum drip line size of 20 ml nominal diameter. As mentioned previously, we have a mixture of A systems, AB systems, and ABC systems, which is determined by the tree variety that is used. These systems are explained in the following. In an A system, a valve is connected to all the rows, submain risers and laterals, with 2 drip lines per row. In an AB system, one valve is connected to all second row, submain risers and laterals, with 2 drip lines per row. In an ABC system, one valve is connected to all second or A rows, submain risers and laterals, 3 drip lines per row. A valve is connected to all fourth B submain risers and laterals, with 3 drip lines per row. A valve is connected to all fourth C submain risers and laterals, 3 drip lines per row. In this example, I've shown one block of the 3 systems. In the A system, the total block area is 3.48 hectares. We have 30 tree rows and 60 drip line rows, with a total flow of 46 cubic meters an hour. The AB system, the equivalent block area 3.48 hectares, but as we're only connecting to every second row, each system has 15 tree rows, 30 drip line rows, and 23 cubic meters an hour. The ABC system with 3 laterals per row, the block area is still 3.48 hectares. The A system has 15 tree rows every second row, 45 drip lines because we have 3 laterals per row, and a flow rate of 34.5 cubic meters an hour. The B system has 8 rows or 24 drip line rows and 18.4 cubic meters an hour. The C system has 7 rows, 21 drip line rows, and 16.1 cubic meters an hour. On some systems, the emitters on the 3rd lateral of each row may be blocked off around the base of the tree. Submain design. In submain design, submain head loss and velocity. Aim for a maximum friction head loss per submain of 3 meters. Maximum velocity in a submain, 2.5 meters a second. Minimum flushing velocity when designing a submain, and in the case of a drip line lateral, 0.4 meters per second for average quality water. A pressure envelope in a drip system. Minimum block pressure, 110 kPa. Maximum block pressure, 250 kPa. When designing a CNL system, minimum block pressure, 130 kPa. Backup filtration. Similar to our main filtration, we also have 3 typically standard options for our backup filtration. Semi-automatic screen, automatic screen, and disc. When determining what style of filter we use, the discussion is normally made with the customer of their preference and also the water quality on site. Mainline design. For any efficient irrigation system, the mainline design is a very important one. When looking at mainline head loss, an economical pipe sizing or capital versus running costs on the larger systems is 0.3 to 0.4 meters of head loss every 100 meters. A maximum velocity in a new mainline system of 1.8 meters a second. A minimum velocity in a new mainline system, 1 meter a second. This is to account for the travel time in fertigation programs, so they are not too long. Mainline types of material, so PVC, typically standard on all irrigation systems, on flat ground within property boundaries. HDPE, typically used for rising mainlines or through cliffs or other rough terrain, or for single mainline requirements for diameters above 600 millimeters. GRP, which is less common, but can be used for larger under-road bore crossings through a HDPE sleeve. The use of ductile iron or stainless steel fittings on any pipework above the size of 200 mm is preferred. This excludes HDPE as we have butt or fusion welded fittings available for these sizes. When looking at mainline layouts, avoiding ring mainlines where possible due to fertigation problems. I have an example to show you of this. We typically design outside of the block boundaries for cases of any mainline breaks and to mitigate potential damage of the crop. Air valves are designed at every high point or in 500 metre intervals. Piping systems 375mm and above recommend a surge analysis undertaken and larger orifice anti-slam valves installed. Purge valves at the end of main lines are to be designed for yearly maintenance or mainline breaks. In this example, I will show the difference between a single mainline system and ring mainline system. In this single mainline system, time to area F, we only have one path for the water to flow, which takes up 36.3 minutes. In a ring mainline system, we have potentially two paths for the water to flow to get to area F. So mainline 1 in the orange is 46.8 minutes to get from the pump to area F. Mainline 2 in the purple is 31.8 minutes to get from the pump to area F. A note that fertiliser will not be applied evenly in a ring mainline situation as travel times are different. Valve assembly. Typical valve assemblies on large irrigation systems are grouped for automation purposes while still taking into account our maximum submain sizing rules of thumb. Multiple valves in the one location save on labour costs for servicing, and manifolding costs are also less. It also minimises the chances of machinery to run into these in the field. All valve set pressures are set for flushing, drip systems in particular, and not just irrigation. Energy analysis. All irrigation systems are checked for energy analysis costs. We can do this for either power or fuel, including diesel consumption costs. Each mainline section can be checked independently for its economical value. Example, the 0.3 to 0.4 metres head per 100 metre head loss. As labour costs are high here in Australia, electrical power and self-sustained irrigation systems are the more preferred method. So power sites over diesel sites is preferred. In this quick example here, I've shown a 100 hectare almond development. Saving 1 metre head friction loss in the main line can save the client nearly $1,500 a year for the bigger size main line. System automation. One of the most beneficial parts to a new irrigation system is a variable speed drive. The benefits of a variable speed drive on the pump system: it lowers the startup current compared to standard direct online, or more commonly known as star delta pump systems. Multiple pressure set points can save on ongoing energy costs. For example, running the higher elevated blocks on one shift compared to the lower elevated blocks on another. It removes the need for a master valve or controlled irrigation start or pressure sustaining valve for main filtration backflush. It also provides additional protection for the pump and motor. Another important factor of system automation is field control. The most prevalent field control now being radio systems. Other field control types can include 2-wire control cable, but lightning protection is required. Multi-core cable systems are typically designed in smaller setups. The benefits of all these types of control are the functions of pump start inputs, water metering functions, and the labour savings associated with the ability to turn on and off irrigation valves using cloud-based software. Thank you for listening, and I look forward to speaking with you all shortly.